Okay, so today we're going to be talking about work and energy. And so first thing, when we think of work, we think of a couple things. One is you have your job, you go to work. I go to work every morning. You might have a job that you go to work to. But in physics, we're going to be talking about a special type of work, and this is what we call mechanical work. So when we talk about work, it's mechanical work only. So we're going to get more into detail about what mechanical work is, but it's not going to be work as in you're doing your homework or you're going to work. It's going to be a certain type of mechanical work, and we have two types. We have kinetic work and potential work, and we'll go into that in more detail later. Okay, so work is only going to be the mechanical work. Well, the formula for work is W is force times distance times cosine theta. And this formula is very similar to the formula for torque, because we studied torque, which is force times distance, but this one is sine theta. And if you remember for torque, the theta was the angle between the force and the distance. Well, the same thing is going to go with the theta here. So this theta is going to be the same angle between the force and the distance. So the only difference between work and torque is going to be torque is sine theta and work is cosine theta. So we talked about before that the maximum amount of torque we wanted was going to be 90 degrees. So sine of 90 is 1, and if it was 0 degrees, then it would be sine of 0, which is 0. So our torque, when they were in the same, when 0 degrees between the force and the distance, there was 0 torque. Well, now we're in cosine, which is the opposite. So when cosine, the force is 90 degrees from the distance, then our work becomes cosine of 90 degrees, and cosine of 90 is 0, so work is 0 if it's at a 90-degree angle. Where maximum amount of work is when the theta goes to 0 and the force is along the same plane or the same angle, 0, as the distance, or cosine of 0 degrees is 1. Our maximum work is going to be at 0 degrees. So it's the complete opposite of torque. The units for work seem like they should be the same units for torque. So the SI units are Newton times meters, which is the same as torque, but now in work, we actually have a word we use. We call them joules, and it's symbolized with a capital J. And joules is named after a physicist. This is a scalar quantity. That means it has no direction. The magnitude is the force times distance times cosine theta. There is no direction. So we think, well, is it positive or negative? We're going to talk about what happens when work is positive and work is negative. It doesn't mean the direction anymore. It actually means that it has a negative value. So what we're going to talk about is how do we know when it's positive and negative. So really work right here is going to be, this person is going to be pushing a box or an object with a force F, and you're going to move it from this position to this position. So it would be force times distance, and then the theta is going to be the angle between the force and the distance. And you can see that the force is here, the distance is here, so they're both on the same plane. There's 0 degrees between the two. So our work is force times distance times cosine of 0 degrees. Well, now what happens is, how do we find out whether it's positive or negative? If the force and the distance are in the same direction, meaning that this object is starting at 0 and is going to end up someplace later here at D. So we're going 0 to D is this direction is the distance, and the force is in this direction, then we know that the work is going to be a positive work. Well, when it's the opposite, if the force is in this direction and the displacement is in that direction, they're opposite, therefore the work is going to be a negative work. And sometimes this doesn't make sense. Well, how can this box move that way if you're pulling on it? Well, we're going to be talking about maybe the work due to friction. So if this guy's pushing this way, the friction force is this way. Remember, friction force always opposes the motion, and so the work due to friction would be a negative work. Okay, so let's actually try an example here, and this is pretty much plugging numbers right in. A man exerts a force of 400 newtons, so that's our given force is 400 newtons, to pull a wagon. The force is inclined at an angle of 33 degrees to the horizontal. So this is our horizontal, and this is our 33 degrees. The man pulls the wagon a distance of 12 meters. How much, oops, I left that out. How much work does he do on the wagon? Well, we're given the force is 400 newtons, the theta is 33 degrees, and the distance is 12 meters. And just to verify, this theta is the angle between the force and the distance. Okay, so work is FD cosine theta, the force 400, the D is 12, the cosine of 33 degrees. It ends up to be 4026 Newton meters. Here's the newtons, there's the meters, and a Newton meter is a joule. So we have 4026 joules. Okay, so let's talk a little bit more in detail about when we calculate work. So there's two ways to do this. When we talk about work, we need to compare every force that's going to be acting on the object. So if I have a box right here, we know we have the normal force that is always perpendicular to the surface. And we have the gravitational force, which is straight down. And in this case, we're going to have a frictional force that's in the opposite direction of the motion. And here we're going to have an applied force that's going to be at an angle. So there's two ways to do this. One is we determine the work done by each force. So I would say, what's the work done by this, plus what's the work done by this, plus what's the work done by this, and what's the work done by this, and then add it up, and we can find out what is the net work done. Basically, what is the total work done. The other way to do it is determine all the parallel net forces, because remember, the force has to be in the same direction as the displacement. So if our displacement's along here, we're only interested in the forces that are along here. So you can see that the normal force does not have a direction along this way, and neither does the gravitational. These two are only in the y. So then all we would do is determine the parallel net forces, which would be the F applied along this parallel, or the X component, and the F friction that's also on the X. Then add those up and then multiply that by the distance. Okay, so let's actually try this problem really quick. What we want to do is the work done by this is going to be, so the work of the applied force is going to be F applied times the distance d, but now we have the cosine theta. Okay, so the applied work here is going to be F applied cosine theta times this distance. And because the force is in the same direction as the displacement, that's a positive force. Okay, now let's look at the, we'll just do the X one first, the friction force. So the work due to friction now is going to be the friction force times the distance times cosine theta. But what is theta? The friction is this and the displacement is that. It's actually 180 degrees, or we can look at it in being 0 degrees. So we can say that it's cosine 0 degrees, but we have the displacement is this direction and the friction force is that direction, which makes it a negative. Now if you had put 180 degrees in there, the 180 would automatically come out negative. Now let's look at the normal force. So we want to know, well, what is the work done due to the normal force? Well, it's the normal force, and in this case, we would figure that out, but we don't have to. We're just going to stay here. Times the distance times cosine theta. Well, what is the theta between this and this? Well, it's 90 degrees. And we know from trigonometry that cosine of 90 is 0, so this whole thing goes to 0. And then we're going to say, what is the work due to the gravitational force? It's going to be the force of gravity times the distance times cosine. And once again, this is this way, this is this, it's 90 degrees, so cosine 90. And you can see that that also goes to 0. So if I want to talk about the net work, it's going to be the work applied plus the work due to friction. So if I add these up, I have F applied, D cosine theta, and work F is negative of the friction force D, and cosine of 0 is just 1. And so this would end up being our total work on that box. Okay, so now we're going to talk a little bit about kinetic energy. Well, we're really going to be talking about energy, but the specific type that we're going to be talking about is kinetic. And there's a bunch of different types of energy. Kinetic energy is one type of mechanical energy. Okay, so kinetic is motion. So we're only going to be talking about the energy of motion, basically the energy of movement. So if something is not moving, it has no kinetic energy. So if a car is sitting in your driveway not moving, there's no kinetic energy. If you're driving down the road, we have kinetic energy. The formula for kinetic energy, and we use KE, sometimes you'll just see K, is 1/2 mv squared. M is the mass of the object and V is the velocity, and it's squared. The units for kinetic energy is joules, same as work, and I'm going to show you why in just a second. This is also a scalar quantity, and just to explain, those of you that are taking pre-calculus know that this is really V times V, and later on you'll figure out that this is two vectors multiplied together because a velocity is a vector. Well, two vectors multiplied together using the dot product ends up being a scalar. So this is the background of why kinetic energy is a scalar quantity. Because it's a scalar, it has magnitude but no direction. Unlike work, it's always positive. You will never have a negative kinetic energy, always positive. Okay, so let's see if we can get into the reasoning why. Work is, it's called the work kinetic energy theorem. And this is very, very similar to the impulse momentum theorem that we talked about, where we had J, which was our impulse, equaled our change in momentum. Well, now we have work is equal to the change in kinetic energy. Well, we know the change in kinetic energy is just the kinetic energy final minus the kinetic energy initial. And using the formulas, kinetic energy final is 1/2 mv final squared. Kinetic energy initial is 1/2 mv initial squared. And so if you can see here the work, we know the units are joules, therefore kinetic energy is also joules. So both of these have the unit of joules. So we're going to take one more definition and then we're going to solve a problem. The definition, we're going to talk about power. The whole situation with work and energy, we are not concerned with how long it takes. So if you hire somebody to paint your house, you are interested in how long it takes them. Because if they're going to charge you $100 an hour, you think, oh, well, that'll be really good. But what happens if it takes them 10 hours to paint your house at $100? And another company says, we'll charge you $100 an hour, but we'll do it in 50 hours rather than 100 hours. So it's going to be, the time that it takes is very important. Well, work and energy have nothing to do with time. So we need something that we can rate how much efficient something is. So power is the rate at which work is performed. Basically, how fast do you do the work? The way we do that is power, which is P, is the work over the time. And the units that we use for that are joules, because the units for work are joules. Time is second, it's joules per second, and we call it a watt. W-A-T-T, and it's capital W. Now you guys have probably seen that in your light bulbs. It'll be a 75 watt light bulb. So basically that's the electrical equivalent of power. It's how much work can be performed in a certain amount of time. And once again, because work is a scalar quantity and time is also a scalar quantity, power is a scalar quantity. So we're only interested in a positive number for that. Okay, so let's try one problem. Okay, on a frozen pond, a person kicks a 10-kilogram sled, giving it an initial speed of 2.2 meters per second. Okay, so that's our initial speed, that's our mass. How far does the sled move if the coefficient of kinetic friction between the sled and the ice is 0.1? Okay, so we're interested in how far it goes until it stops. So we know that the V final is 0. Okay, so here's a picture. So this is the sled. The forces acting on this are going to be the force of gravity, which is down, and then the opposite is the normal force, which is perpendicular. There's no force coming here, we just have the guy who kicked it, and it already has an initial velocity going this way, and then we have the friction force, which is opposing. So what we're going to do here is we want to look at, if we want to find out the distance something's moved, we know that the net work is equal to force times the distance times cosine theta. And what we're looking for is this D right here. Well, we also know that the net work is equal to the change in kinetic energy. Okay, so if I know that the force times the distance times cosine theta is going to equal to 1/2 m V final squared minus 1/2 m V initial squared. Okay, so now let's fill some things in. The force that we're interested in has to be in the direction of the displacement. So the sled is going to be moving this way. So its displacement is going to be from here to here. So the only force that is in that direction is going to be the frictional force. Now we can go ahead and do these, but we know that the angle is 90 degrees and cosine of 90 is 0. So the only force here we have is the friction force times the distance, and this is what we're looking for. The theta is 0 because the friction is that way, and these are 180 degrees different, so we can say it's cosine of 0. And it's negative because the displacement is this way and the friction force is that way. And this has to equal 1/2 m V final squared minus 1/2 m V initial squared. Okay, so let's kind of clean this up a little bit. First off, let's look at, well, we'll clean this up first, and then we'll get into the friction force. This is what we're looking for. Cosine of 0 is 1. 1/2, the V final is 0, so that goes away, equals 1/2 m V initial squared. Well, we know the mass, we know the V initial. What we don't know is the friction force. So we're going to take a little segue over here and figure out what is this friction force. Well, if you remember, the friction force is equal to the normal force times the coefficient of kinetic friction. The normal force, if we look here, oops, I didn't mean that, that was, should have said, this is the one we're looking at. The friction force equals this. The normal force is equal to the gravitational force times mu, just because the sum of the forces have to be 0, and gravitational force is just the mass times the gravity times mu. So now we're going to put this in here. So where we have this value right here, we're going to replace it here. So we have negative mg mu times the distance, that's what we're looking for, equals negative 1/2 mvi squared. Well, right here, the negative m's can cancel out. So we have g mu d equals 1/2 v initial squared. So d equals 1/2 v initial squared divided by g times mu. So now if I plug in numbers for this, I have 1/2 v initial, which is 2.2 meters per second, over g, which is just 9.8 meters per second squared, times u, which is 0.1. And if I calculate this all, it ends up being 2.5 meters. So that's the distance that's gone. Okay, so we know that it has moved a positive 2.5 meters. Okay, so let's just kind of take this one step further and let's just kind of look at this exact same example. And if I wanted to know, well, what is the power consumed by moving that sled? So I'm going to take it one step further. The power is the work over the time. So what happens if the whole movement of the sled takes 10 seconds? So we have t equals 10 seconds here. what I want to do, the work is right here, the FD cosine theta over the time. Well, the F we calculated here was just mg mu, the force of friction mg mu times the distance cosine theta, all over the time. Okay, so if I plug this in, we know the mass is 10 kilograms. We know gravity is 9.8 meters per second squared. We know mu is 0.1. We now know the d because we solved the d, which is 2.5 meters. And cosine theta is just 1 because the theta is 0 degrees, and it's all over 10 seconds. And so if you calculate it, you could figure out the power. And I don't have that done offhand, but if you just plug that in, you can find the power, and the power is going to be in the units of the watts. Okay, so that is all we have for today. Don't forget the video for today, don't forget the lesson for today's video, and we'll see you tomorrow in class.